Okay, all right, everybody, let's get started. Okay, so this is the final session of the day. So the session is broken up into, well, I was originally broken up into like 3 distinct pieces, but we changed it recently. So like first we're going to talk about, I'm going to introduce like what I/O is and why we want it. And then Art is going to talk about some of the definitions of I/O. And then Jay is going to talk about this specific scheme that we've implemented called local mixing. And he will describe the bounty and talk about that. And this is supposed to be, and then Tianyao is going to talk about Oblivious RAM and how you can build memory to work with I/O. So that you don't have to use a circuit model, you can use like a more computer model. And that's our plan. And then I was supposed to finish about like 3:30, 3:45. And yeah, so this is supposed to be interactive. We have whiteboards and like some slides, but mostly whiteboards. So please ask questions as we're going. Arturo's running around with a mic if you put a hand up, or you can just shout things out and we'll repeat the questions. The most important thing is that we have like a dialogue, so we're able to explore these things together. So that's our plan for today. So let's get started because we're a little bit tight on time, it seems. Okay, so let me start with my piece about like I/O and why it's useful. So I kind of talked about this a little bit earlier, right? So what do we want to do when we do I/O? So we want to take like a circuit, some kind of computation that we want to do that has some inputs and some outputs. Like imagine that this is like an AND gate where you have like 2 ins and 1 out, okay? Merge these together. And then the truth table of an AND gate, I know, is this. Yeah? Anyway, so like we have some kind of like circuit that we want to execute. So the people over there able to see. Is everyone able to see them? Is it better like this? Is that good? Alex, can you see this? Yeah? Yeah. It's okay? Okay. Okay, so this is what we start with, right? This is the, like kind of the input that we want to obfuscate. And then we have some process here. This is the obfuscation step. And you can think of this like encryption, that we want to encrypt this program such that on the other side we get something that preserves the functionality of the program but has a different it preserves the input-output map, but it has a different, all of the intermediate steps are hidden. So all that I can learn from this program is what I can get from like a black box access to the program. So imagine that I'm able to like, imagine I put this on a server and I'm able to execute this circuit on a server, and all I'm able to do is learn like for what input I get what output, but I'm not able to learn anything about what's happening internally. So that's the goal, that's what we're looking for here. And let me explain why we're looking for that. Okay. So the reason that we're looking for that is we want to do things like, we want to make an I/O box. Yeah? We want to make this like encrypted box that I can send to you. And you're able to like execute the box, you're able to give inputs and get outputs, but not able to learn what's going on inside. And specifically, what we want to do is we want to have a signature. And we want to have an encrypt and a decrypt happening inside this box. And then we also want to have like just general compute. We want to have all of these things happening inside this I/O box such that you're able to encrypt, decrypt, sign things, but you're not able to see the private key that's doing this. You're also not able to see the intermediate steps. So like imagine that I have here's a simple I/O box we would like to make, right? You give an encrypted input, input 1, and I give an encrypted input 2, right? And the I/O box takes the inputs, it decrypts input 1, it decrypts input 2, it adds input 1 plus input 2, and it returns the result. Right? Or like, let's say instead of add, it multiplies. And this is really powerful. Like if you can do this, then you're able to do like all of that stuff you can do with FHE and all the stuff you can do with MPC. But you're able to do it in a non-interactive way. That I can encrypt my thing and I can just give it out to the world. And then the world is able to take my thing and it's able to do like arithmetic to my thing, or it's able to execute any program on my thing and just return the output just return the output transparently. So that's our goal, right? Because like last year I talked about like 2PC is for lovers, which was talking about like MPC applications and how you can build things with MPC. But like the problem is that it's interactive. You have all of this power, but like you're really limited because of the interaction. The key to the interaction is not the annoying user experience. It's the upper bound that it places on the size of the computations that you can do. Because if you need to have an interaction to decrypt, that means that the maximum number of participants is bounded. It's bounded by the maximum number of people that can be online at the same time. And that means that like you just have this upper bound that you're not able to get over. Like you can have a hallucinated server with like 10 people, maybe 100 people, but you can't have one with 1 million people. And that's what we want to do here. We want to be able to make these hallucinated servers with millions of participants, and that's why we need I/O. So this is the motivation for I/O. So now I'll pass over to Ard, or to Jay.
What is hallucinated server?
What's hallucinated server? Thank you for the question. So hallucinated server is like an abstraction for like a group computation. So like imagine that like normally when you do a computation, you send it to like a server. You send it to AWS. And AWS takes your thing and it does the computation. Hallucinated server is a server that no one can see inside. That like it maintains the authenticity and the reliability of a like Amazon Web Services server, but it also has the extra guarantee that like no one is able to see the intermediate steps. No one is able to fake what's happening inside the server. So like it's kind of like another way to think about this is that like what I/O lets you do is it lets you to simulate like a trusted third party. It lets you to make up this trusted third party such that you're able to such that it can do anything that a person can do. Yep.
Do you want to go into the difference between I/O and virtual black box obfuscation, which is like this is something you're planning to do, or
no? That's Aaron's plan.
Okay.
Yeah. Yeah. Do you want to take it?
Sure. So, okay, so the next 5 minutes or so are going to be a teeny bit more Hello, okay, is that better? Yeah. No? Okay, the next 5 minutes or so are going to be a teeny bit more technical. How's that? Okay. But the takeaway is if you zone out for the next 5 minutes and you wake up at the end of it, you won't miss anything important. So the thing we want is called black box obfuscation, maybe virtual black box obfuscation. And the punchline is you can't have virtual black box obfuscation, but I'm going to tell you about it anyway because it's a useful thing to keep in mind. So what does this mean? Black box obfuscation means I have some program. Let's say I've implemented some function, call it f. Maybe it's computed by some circuit or some piece of code or something. And so I have this function f, which has some functionality. If you feed in these inputs, it gives you these outputs. And I also have kind of my implementation of f, which maybe it has some secrets inside. I mean, maybe f is some sort of cryptographic thing, and maybe it issues signatures, and the implementation of f has inside it a private signing key, for example. So black box obfuscation, if it existed, would be an algorithm that takes the source code for f and obfuscates it. So you get some obfuscated f. And this is another, I don't know, it depends what you want. If you want to think about circuits, f is a circuit and the obfuscation is another circuit. If you want to think about programs in your favorite language, f is some source code and the obfuscated thing is some source code again. So whatever it is, it gives you another program that has exactly the same functionality. but with the property that you can't learn anything about F. You can't learn anything about the original implementation just from looking at the obfuscated implementation, except for, of course, what you can learn just from feeding in inputs and outputs. So, for example, if F was a digital signature issuing program, well, you can't learn the private signing. You can't learn a private signing key just from a lot of digital signatures. Even if you have black box access to a signing machine and you can, adversarially make up as many messages as you like, you still, we assume, can't learn the private key. So if black box obfuscation existed, then the security condition I require is that you can't learn the private key from the obfuscated code either. Okay. This is what we want, and we're going to pretend we have this. This is called black box obfuscation. The fact of the matter is you don't, and there's a proof of impossibility. You can write down, there's some sort of silly diagonalization argument thing. You can write down a very contrived example of a program F that can never be obfuscated because there's some argument involving, you feed F its own source code or something. There's a sort of very contrived example that rules this out. But let's pretend we, let's not think about that for a minute, and I'll say why. There's a weaker version of obfuscation, which we think is probably achievable, called indistinguishability. Indistinguishability obfuscation. So black box obfuscation was the obfuscated program teaches you nothing about F. Indistinguishability obfuscation is a weaker requirement. It says if you have two implementations of the same function and you obfuscate two implementations of the same function, you can't tell them apart. So there's a function there you could imagine. There's many ways you could achieve this functionality. There's many ways you could code it up. But if you have any two implementations, as long as they do the same thing, when you obfuscate them, you can't tell them apart anymore. Okay. So that's maybe interesting. I don't know, a question for you. Can you think of anything exciting you can do with indistinguishability obfuscation? Yeah?
If you have an example of a non-Turing system, we have a loop, a function in which we are calling a loop, and let's say it's a smart contract and it is just keep on going. And we will have like two smart contracts with similar function. So will this I/O can distinguish, or maybe we go with black box in this approach? I don't know.
Say again, you have two smart contracts that both do something in a loop. Do they do the same thing? Okay, it seems to me if you had two smart contracts that did exactly the same thing and they both obfuscated their code, then you wouldn't be able to tell which code is which. Is there any reason you want that?
Yeah, I want if, let's say, a smart contract in loop keeps spending gas and it's not finished, then we are able to distinguish because it's not complete. It's just keep running the loop. So
maybe let me try and repeat to see if I understand what you mean. So you have this kind of like auction thing that's running, and like the auction thing is inside a while loop, and like you don't want anyone to know when the auction is about to finish, because if someone knows when the auction is about to finish, then they'll be able to like gain some kind of advantage. So you obfuscate the program such that the auction keeps running and running and running, but like no one knows when it's about to end, so they can't put the like bid of like 0.1 more than the previous bid or whatever.
I mean, very better example than me, yeah, if you can follow up with that. So.
Okay, yeah, I think that's a like spiritually what you're trying to get at here.
Yes.
Yeah.
Yeah.
I get the answer.
Yeah.
Sure. I mean, okay, this is the sort of thing you want to do. It's definitely the sort of thing you could do with black box obfuscation. Yeah, but coming back to I/O, like the definition of I/O makes it seem kind of useless. But in practice, there's a trick that whenever you have something you can do with black box obfuscation, that you can also achieve the same sort of thing, assuming I/O. So there's some sort of trick involving, I don't know, some sort of punctured pseudo-random functions or something. I don't want to get into it, but we're gonna sort of do a bait and switch and say, okay, we want black box obfuscation. We're going to talk about applications of obfuscation as if we had black box obfuscation. But then when we construct something, of course, the only thing you can actually construct is I/O. And so, yeah.
So it means for practical purposes, you would say the differentiation between the two is not important, like the usability of I/O. Like I know a bit about I/O, I've seen some of the proofs, and it seems quite technical to make it work in the end, to get these constructions to work. And I was surprised to hear that it's sufficient to actually build practical things in the end, but it seems like maybe not an issue. Or like you can actually use it as a tool immediately. That's what you're proposing? I/O? Or not?
No, we are not proposing that we can use it right away. What we are saying is there are new approaches to program obfuscation, I/O, which lie under the spectrum of, let's just say this is a spectrum. Less practical, more practical, less secure, more secure. We are at this end at the moment. What we've done is like we've taken a practical scheme of which the security is not that. We are not able to speak much about the security of that scheme, but it's practical. We can go the other route as well, where we go to the standard assumptions, and that becomes not practical.
I was not even worrying about the assumptions or the
Okay, I
security,
see.
more about actually the usability, independent of whether the implementation is secure. But maybe you can
When you say
go ahead and
I
then...
see. Yes, so assuming you have I/O, the question is what can you build on it?
Exactly, because
Oh,
for
I
me
see.
it wouldn't be, like I have a relatively clear idea of the formal definition, but for me it's not so clear what you can actually build with it if you have it. Like,
Right.
of course you can like make these constructions work, but as you said, the technical details that you need to go through to make it work is not like trivial to me. So I was surprised to
No. Okay, but I agree with you. I mean, I think the situation is if you could do it with black box obfuscation, you can probably do it with I/O as well. There's a bunch of technical details that are difficult that we're not talking about.
Is your question like in general, if we could, like what would we do with it? Oh well, there's so much stuff that we could do with it. Yeah, it's like the final piece of cryptography. Like, yeah. It's a technical argument. They're the same thing. It's just this weird technicality.
let's just do one thing. Let's just give an example. Do you want to go ahead, or should I?
He's not asking about like what would we do. He's saying that like, well, black box obfuscation is clearly useful, but I'm not sure about indistinguishability obfuscation.
I agree. It's not obvious to me either.
I disagree. I think it's just a technicality between the two.
I just want to try, see if I can clarify the question. So it's not even really my question. I'm trying to answer, clarify this one. If I have black box obfuscation, everyone agrees that's pretty obvious. If I have this ability to do this I/O thing, I'm going to need two different circuits, and both of them, like if I'm trying to do this with something that can do a signature, both of them are going to reveal this, the private key, right? So now I can prove, oh, I've made some, I can use an I/O version of this to get an obfuscated version of each of these two things. Oh, they get the mood lighting, nice. And now I have two different versions of a circuit that have been obfuscated, and I can't tell which one is which. But I'm still not mapping it to an actual useful circuit.
The point is that you have two versions of the same thing, and you can't tell the difference between the two. It's a definition. Like it's trying to show you like how this is useful. But like the point is that like the two things are not like, oh, you can't tell the difference between the two. The point is that you can't see inside what's happening. Like for me, the I/O thing is just like a definitional part. Right. So we need to.
Let's just stick to like a few minutes more to this. Let's just try to stick to a few minutes more to this. What we can try to do is, okay, what are the two properties that I/O sort of guarantees? It's like if you take a circuit and you have an obfuscated function and you produce an output circuit, you take the same circuit again, do it the second time, and produce another output obfuscated circuit. These two circuits must be indistinguishable. That's sorry. Oh, you had a different question? Okay, different question. Cool. Yeah. So they're indistinguishable. It also guarantees that it is indistinguishable from the original circuit, right? Yes. Okay.
Yeah. Can I maybe try saying like one thing about like a hand wavy mental model that I have? So like I think the claim is that if you have some obfuscator that satisfies those properties of indistinguishability obfuscation, it quote unquote basically acts as a black box obfuscator. Like you can use it with the same API as a black box obfuscator. If there is something that satisfies that definition, it's like more or less a black box obfuscator. And here's like one way to sort of hand wavily see this. So imagine all of the circuits that you could possibly write down that are equivalent to the function that you're trying to write. Like most of those circuits are actually like really complicated and nonsense looking. And it's like really hard to derive the functionality. Like just try to imagine like all the strings that when interpreted as a Python program implement a given function. So most of those strings are going to look like really, really crazy. So if you have indistinguishability obfuscation, then what that's sort of saying is that if I run the Python program through an obfuscator, I'm going to get just like one of those strings, and I'm not going to be able to tell which one of it is. And if we believe that most of those strings are really hard to back out the original program from, then I'm basically happy with this as approximately thinking about it like a black box obfuscator. Does that sort of?
Sora has a question.
Yeah. So intuitively, I see the value of the indistinguishability obfuscation, although there is some vagueness of what exactly we define as indistinguishable between what exactly, because like doing the same thing is like on the level of design, it can be like if it's a very, very same thing, then it's a very, very same way of doing it. But if you're doing it differently, it's slightly different thing, right? Achieving the same goal, but like it's a level of definition. But anyways, like my question was, do we have an idea how to get IO?
The short answer is yes.
Yes.
The short answer is, first of all, we have a precise definition. You might not like our definition, but if you have, I mean, when I say you have a function takes some input, maybe it takes bit strings of length 1,000 and gives some output, maybe a bit string of length 20. And if to say it does the same thing really literally means whenever you feed in the same bit string to two functions, you get exactly the same output. There's no wiggle room. And so fine. So that's the definition, is that when you obfuscate a program, you can't tell the obfuscated code from an obfuscation of any other program that does exactly the same thing. As far as how to get I/O, there are a bunch of approaches in the literature. There are some that are proven secure, but are too slow for practical use. There are some that the security is kind of an open question, but that appear to be practical. But then you have this question of, is it secure or not? So that's sort of in a nutshell the state of things right now.
Can I give an answer to your question earlier about like two programs that you would put in and just get a little more practical here? So let's say I have two programs, and let's say that one program takes as the input like some string and then adds a secret value to it, hashes them together, and outputs the hash. And let's say the second program takes as input the string and then like iterates like 1 billion times until it finds the thing that matches the hash and puts it out. So those are going to have the same inputs and the same outputs, but one of them has like this observable property that if you could see it, then you could do the computation more easily.
I disagree, because how did you implement the second program? The second program does, did you just say it kind of does random guesses until it happens to guess upon the hash? And then it compares each of its...
It iterates over a sequence of numbers that would, it's a long list.
But how does it know, the second program, how does it know when to stop?
It has a matching, like it has half the hash that it's matching against or something. Like the example is not important. The point is like you can write an example that one version is like the trapdoor function that has the easy way to do it, and one is the brute force version that takes longer but gets the exact same output.
I see.
And the indistinguishability property is interesting amongst these because in real life, if we could observe the internal difference between these two functions that have the same input and the same output, we gain insight into something.
I see. Okay, cool.
Can I be more specific with that? Can I say that it becomes interesting when you're having some cryptographic function inside it, right? And eventually that gives you something like a black box obfuscation, because now you have a function. You have a function inside this thing that is that still preserves information, but it structurally destroys it, right? I think. Okay, it's not. Yeah. Does that make sense? Does that sort of like comprise the answer?
Yeah, like the point being that if you're feeding in the one that has the like easy code that does it the really easy way, that result is going to be indistinguishable from having fed in the code that does it the really hard way. So that's the computational edge of the obfuscation compared to somebody who doesn't know what you put in.
Yeah. Thank you. I think there are more people. There's one.
So, sorry.
Oh, yeah, go ahead.
Sorry. So from, let's say, a very practical point of view, if I want to explain to someone what's possible to do with the tech, could I informally say, imagine you have a cryptographic version of a TEE, and that's pretty much what you can do, like some hardware that you really, and there is not even a side channel, anything that's possible to do. You just put the inputs, it's something's going on, it's going to spill out outputs.
Yeah, I would say that I would call it a mathematical DA.
Thank you.
Right.
Thank you. So is it correct you claim that even if indistinguishability obfuscation does not directly guarantee black box security or indefinition, you think this can be, IO can be in practice regarded as a kind of black box obfuscation, right?
As long as you have something, like, as long as the function inside this is cryptographic function, something that's sort of like it's hard to reverse from input output map.
So you mean like if the function is like such that if the given input satisfies now some condition, this is signed by the embedded hard-coded private key. So do you think such function can be also, IO for such function can be also regarded as a black box one? So I think there is so I don't think IO directly implies a black box condition even for cryptographic functions, because there is a construction called IO kind of obfuscation called ideal obfuscation, which achieves the black box security formally, but assuming the heuristic assumption like a hash function is a kind of random oracle things.
When you say ideal IO, do you mean same size?
Not same size, because in the ideal obfuscation, we also have to compute the kind of hash. So it slightly increase the size and the computation cost from IO. And this hash function is necessary to achieve the black box security formally.
Probably, okay. I would say that I still don't understand what you mean by ideal IO.
You should take this technical discussion offline. I feel like it's useful for like a small group, but it's not useful for everybody. So let's talk with them.
The general goal of this is like to get an intuitive understanding of how can you use it for a black box thing. I think using putting cryptographic algorithms inside the IO box gives you something like virtual black box. It may not satisfy cryptographic definitions, but intuitively you can use it as a black box. Like when you think of like APIs, it's like a black box, like a mathematical TE. I think Oscar had a question of that.
Yeah, so my question, so from Barry's presentation yesterday, my understanding is that there are different assumptions, and the most exotic assumptions are basically something that makes some IO kind of feasible. So first question is like, what is the nature of those assumptions? Like, I have no understanding of that. Like, that would be the first question. And the second question is like, what is it about the more exotic assumptions that makes it that we can actually start to work on these things?
Can you repeat the second question?
So what is it about the more exotic assumptions that allow us to sort of start to construct these things that is not possible with the more standard assumptions?
Okay, I think, sorry. Okay, so the first question is, what are the properties of these new assumptions? And the second question is, just correct me if I'm wrong. The second question is, what in these assumptions allow you to achieve practical IO at the moment, right? Okay. I would answer those questions right like after this, once we're done with understanding the examples.
I think that we should move on to that now because it's 5 to 3.
Okay. Cool. Are you done, or do you have something more? Yeah. Oh, you're done. Okay, cool. Okay, let's just try to erase this thing, and then let's get started. Okay, so I would be talking. I would essentially be answering those two questions directly, and to do that, I would be describing you one way of achieving something like indistinguishability obfuscation. One way of achieving that, and just to reduce the complexity of the entire explanation, I would be restricting myself to just a very specific class of functions. And those class of functions are random permutations. When I say random permutation, you'll think of a bit string, which is like 0, 1, 0, 1, 0, 1. You perform some function on this bit string. And this is the function I'll be describing to you now. And you get an output. I'm claiming that the output bit permutation is indistinguishable from a truly random permutation. And what do I mean by truly random permutation? Well, a truly random permutation is like the permutation you get from a bit string that you get from entropy source. Like, some sort of heat or something like that from laptop. Okay, make sense? Truly random permutation makes sense? So I will be restricting myself to building. Question?
The string.
Yes, like permute it somehow.
So permute means mix up.
Yeah, mix up. Yeah. I would be restricting this class of function, and later we can talk about how this is useful and how it will apply for getting general class of functions, like getting IO for general class of functions. Okay, that's good. Cool. For this, I'll have to first introduce a bunch of concepts, a bunch of words that I'll be using throughout. And if I miss explaining some words, just raise your hand and sort of like answer those questions directly. And the scheme is called local mixing. The first thing that we need to learn about local mixing.
Input to the scheme.
What's the input to the scheme?
Yeah, what do you start with?
You start with a bit string.
A bit string?
Yes.
What does bit string mean? Like, what is that useful for?
Bit string is the input. Like, I'm restricting myself to this specific class.
I thought we were trying to obfuscate programs. Well, you're talking about bit strings as an example.
Yes, I'm restricting myself to a specific class of programs that works with bit strings. Well, any input to any function is a bit string, right?
Right.
Like bunch of 0, 1, 0, 1, 0, 1, 0, 1.
Yeah.
Yeah.
So it's the input that you're trying to obfuscate.
No, I'm trying to obfuscate a function that performs random permutation on these bit strings.
Oh, so you have a random shuffle and you're trying to obfuscate the random shuffle?
Yes.
Okay, so the bit string is the input.
Yes.
The program is the shuffle.
Yes.
What's the output?
Another bit string.
Okay, so the output is another bit string.
Yes.
Well, like, you're trying to obfuscate the random.
Yes.
shuffling.
Okay. Yeah. Okay. Does that make it clear? Thank you, Barry. Okay. This is called local mixing. Before I sort of like talk in depth about local mixing, the implementation itself, I need to introduce you something called reversible circuits. How many of you guys are familiar with reversible circuits? Okay, I think I need to explain reversible circuits. Okay, reversible circuits. Okay, fine. A slight deviation from the main thing. A reversible circuit is a way of expressing a computation such that it can be reversed. Okay. Let's just say A plus B is equal to C. I write a Boolean circuit for calculating A plus B is equal to C. And if I give you C, can you find what A and B are from C? No? Oh, yes. It depends. I've only given you C. Yeah? Yes, yeah. You can never figure out what A and B are if I just give you C. But if I give you, so this is an irreversible computation. Okay? Now if I give you C and B, you can find what A and B are, because I've already given you B, you can find what A is. This is reversible computation. And people started investigating reversible computation, and they came up with a way of expressing general reversible computation via something called reversible circuits. Okay? What are reversible circuits? I'm going to draw a bunch of things over here, and then I'm going to explain what it is. Okay?
8 minutes left.
Yes. Okay, so let's just say we have a function, and that function is gates. These are the gates. Okay, we have got let's say 4 gates. This function computes on a 4-bit input, 4 wires. Okay? A reversible circuit is defined by number of input bits, number of wires, and number of gates. Each gate permutes the wires in a certain way. And I would restrict myself to a specific type of gate, which is usually referred to as a Toffoli gate. A Toffoli gate takes, let's just say there are many wires. It takes 3 of those wires. The difference between these 2 wires and this wire is that these 2 wires are called control wires, and this wire is called the target wire. Okay, so it can select randomly. A Toffoli gate sort of like selects among all the n wires 3 wires. 2 of them are control wires, and the third one is a target wire. What it does is that let's just say this wire is A, this is B, this is C. What it would do is that it will take A and B, perform some control function on these 2 wires. What is a control function? Could be AND, OR, and any arbitrary Boolean function that you want on 2 bits. It performs some control function and XORs it with C and sets C as that. Okay? So you realize that this particular gate, a single gate, only mutates 1 wire. It is only mutating C based on the values on A and B. Okay? And you have a bunch of these wires, like many of them, to compute any function. Clear? Huh. Now what local mixing approach does is that it observes one special thing about these functions. It observes that if you have many gates, let's just say you have n cube gates. Well, no, let's just do n square. If you have n square gates with 3-bit permutations, what essentially happens is that the input and output are, the output is a strong pseudo-random permutation. So let's just say we have a reversible circuit with many, many gates, and each gate is a Toffoli gate, which is like this gate that I described. If you have a bunch of them, then the output that is computed on a given input is indistinguishable from a 2D random permutation. Okay? That's what, and this is the basic property that local mixing approach leverages to build program obfuscation. Okay? Is this clear? Because this is the key point in this entire approach. And the entire paper or the entire approach can be described as, making assumptions to make this work for program obfuscation, honestly. They're making a bunch of assumptions based on this property, and they're trying to, and they're constructing, and they're trying to use this property and make a bunch of assumptions to build program obfuscation for any arbitrary thing. Okay? But this is the key thing. Sounds good? Permutation function looks like a single gate or the entire. Okay, let's just say you have this as the reversible circuit, and you have, let's just say, 4 wires here, 5 wires here. Now, let's just say this is M, which is equal to n square, and we are claiming that this is enough to build a reversible. This is enough to make this reversible circuit pseudo-random permutation. Okay, so what it would look like, let's just say you have a bunch of inputs, 0, 1, 0, 1, 0, 1. It will produce some output, 0, 0, 0, 1, 1. This is indistinguishable from a random permutation that you choose from entropy. When I say indistinguishable, let's just say the distance. When you measure the distance between the 2 strings, the distance would be less than certain value.
The overload in the word permutation here.
Okay.
Because like you originally started to trying to make like a random permutation, like to mix up the inputs, but you also, when you talked about the Toffoli gate, that does a permutation too, and I feel like this might be some confusion here. That like the gate itself does a permutation, but all the gates together do another kind of permutation.
Yeah, which is induced by the gates themselves. Okay, so first thing to note is that the authors use this paper sort of like this particular approach sort of uses this pseudo-randomness property of reversible circuits. Okay, long enough gates, pseudo-random. Now, what they do is they sort of like express their entire compute let's just say okay, let me do this. Let's just have circuit C. What is circuit C? Again, a reversible circuit. And this is again with m is equal to n square, and n is like number of wires. What essentially the approach does is that it takes a local subsection of the circuit. Now imagine this particular circuit is very big. There are many gates. It'll take a small subsection that can be replaced. When I say replace, just intuitively understand it like you can take it out and replace it with something else. Okay, it takes a small section of the circuit and then replaces that particular small section with another reversible circuit that has more gates. So let's just say it takes out, with the same functionality. Okay, so it takes out, let's just say this subsection, we call it circuit out, and then via brute force comes up with another circuit, Cn. Let's just say this has 3 gates. That Cn may have, depending on the parameters, let's say 5 gates. Okay? So Cn has like 5 gates, but it is functionally equivalent to C out. And with f of v, I mean functionally equivalent. Okay? So it takes the subsection out, replaces it with Cn, which is functionally equivalent. Now think of this as introducing redundancy to the circuit. We are adding more redundancy to this particular circuit because we're taking small subsections at random, and we're replacing it with more gates. Okay, so let's just say that we do this for many times, 100,000 times, 200,000 times, depending on the parameters. Is this enough to obfuscate? Like, is it easy for you at the moment to reverse this operation?
Until now?
Can you say that again?
What have you done up until now? You've just taken you just take pieces of the circuit and replace them with really big other pieces.
Yes, I've just introduced same functionality. So
Right.
I've selected local subsections and replaced them with bigger circuits.
Yeah, but surely you could just go the other way. You just kind of recompress it, right? You take all the big sections and you replace it with smaller sections, right? You can just go through and see oh, what's the smallest possible section I could replace this with? You can just go the other way around.
Right. What Barry is trying to say is that you know that I've taken C out with 3 gates. I've replaced it with C in with 5 gates. What you can do is that you can find random subcircuits, random local subsections with 5 gates. Try to brute force and find their equivalent circuit with 3 gates and reverse the operation. Okay. I'm sort of like, okay, go ahead.
Be known by the attacker. So the attacker is supposed to know that your replacement rule is that you're going from C3 to C5.
Well, yes, but not necessarily. That's not necessary. Even if you hide it, I think there's an attack. Because let's just say the attacker does not know 5 and C. Intuitively, if you know about a complexity, obviously the class of functions that C out computes, like any class of functions that with 3 gates, they're easily computable by 5 gates. But it's always not the other way around. Like class of functions computed by 5 gates may not be computed by 3 gates. So while you introduce the redundancy, you're adding these redundancy parts, and you're sort of like introducing hotspots where attacker could brute force and find the subsections that compute class of functions computable by 3 gates with 5 gates, and figure out what the values are. So I think there's an attack without that as well. The questions over there.
In the expanded bits of circuits, like, shouldn't you be able to identify, well, shouldn't you be able to recognize when there's some like trivial stuff happening, like multiplying by identity and things like that, yes, and just kind of like whittle it down until you get back to the original small circuit?
Right. That's a good point. Yes, I think that's an attack as well, and I'll describe you how to get around that. There was another question from me.
I guess it's pretty much the same question that I think Barry mentioned it as well. Like to me, intuitively, it seems to be compressible back, because if we iterate through a set of gates like this circuit, we could identify parts of the circuit that could be implemented identical with the identical function, like inputs, outputs, identical with less gates. And if we do that enough times, then we would end up with the, presumably, I guess, the original circuit.
Right. Okay. You're right. So just for everyone, what they're saying is, let's just say you have gate 1. Let's just, okay, sorry. I should not be erasing this, otherwise I'll need it again. Okay, what do? Let's see. Let's just say C out is G1, G2, G3. Okay? G1, G2, G3, sorry.
You have 10 minutes left.
Well, I need to explain all these things, otherwise it's really hard to make a jump.
I understand. I'm just telling you the time.
Okay. I'll quickly go through this. Okay. So you have C out, G1, G2, G3. If I come up with C in, with high probability what's going to happen is that I'll come up with a circuit, something like G1, G2, G3, and another gate that is like I and I inverse, right? With high probability, I'll come up with something like this. And that's the exact attack that you were describing, that with high probability, a replacement operation would be like a bunch of the same gates with identity inverses, or some inverses like gate, inverse, gate, inverse. Is that correct? But in general, but like, if you do not, have a way of getting around this problem, then with high likelihood, most of our circuit will look something like this, right? And essentially, the introduced redundancy would be useless. The way we get around this problem is that, we come up with a way to we do not, okay, so the way we get around this problem is like, it's quite simple. You just come up with a way to represent the selection algorithm such that these cases are avoided. Like you come up with a new type of representation of this reversible circuit. And the way you represent it is via dependency chains among the gates. And you take, okay, this might not be clear, but like you take convex subgraphs of this dependency chain, and then replace it with something else. But I suppose explanation cannot be done in like 10 minutes for this. But like we get around this problem by coming with a canonical representation of the reversible circuit so that we get around this edge case where we are just coming with inverses in the same gates. Okay. Now, essentially, probably in the representation that I have implemented in the actual implementation of this for the bounty, this might exist. And probably there's a chance for you to figure out whether this exists or not. Cool. So what do? We've introduced a bunch of redundancy, which is okay. Oh, there's a question over there.
Hello. Yeah. So just going down to the very basics, and I am assuming that we are talking in a theoretical sense here in terms of what attacks are possible. So if someone has access to the circuit and they know how many inputs there are and how many, like what the entire circuit, and if we are just talking about gates, it is possible to construct the Boolean expression for the entire circuit, and then you can just use Boolean algebra to deconstruct it into the simplest form possible. And then wouldn't that be equivalent to the functionality that was originally intended?
No. Well,
it depends on the number of inputs. So basically, we're talking about cases where you have like 256 inputs, binary inputs, and in that case, it's not possible to come up with the whole truth table. I think this is what we were getting at earlier when you were talking about cryptographic functions.
It's like, it's really hard to, so let's just say your function is very trivial. Let's just say your function is a plus b, then obviously it's reversible, right? Like the moment you have input-output map, you can run Boolean optimizer and get back the function. But let's just say your function is SHA-256. Well, it wouldn't be SHA-256, otherwise you would know it, but it's sort of like a cryptographic function. Then you cannot find what the function is, right? Yeah. At a certain scale, I mean, you can, like it is only useful for class of functions where you can learn the function only by brute force. And for brute force to be, feasible, like for this to be anything interesting, you require the input break string to be really big. Let's say 64, 70, or 80, or 256, whatever that is. Okay, yeah.
Maybe again a basic question, but does practicality also take into account the performance of the obfuscated program or not? Like, does the literature ever analyze what is the code size of or the memory footprint or the execution time of the obfuscated program? Because if I want to deploy that on AWS, but it uses 100 terabytes of RAM, then maybe I'm going to pay a lot.
Right. That is true. So if you go to the algebraic way, which is most secure way of doing a program obfuscation, it is literally 100 terabytes. But when you go to this more sketchy side of program obfuscation, where we're using some sort of like complexity arguments to obfuscate a program, and output something that cannot be reversed, then it becomes more practical. For example, the obfuscate circuit that we have published for the bounty, it executes within milliseconds. It is not that big. It's roughly at 200,000 gates, sorry. So it has roughly a blow up of 200x, which is, depending on where you, like if you're coming from, normal software engineering, probably that sounds not that good, but like in cryptography, that's good.
Yeah, so just to get in the right mood, if I understand correctly, the extra assumptions you have on top of the standard ones are related to the fact that you can make this exact transformation that extends the circuit in a way that it cannot. Example, like difficult SAT problems to solve or something similar to this. Like,
okay. Okay, so what if we have introduced redundancy? and then after that we can chat offline. Okay, so trust me at the moment that I am going to. There is a way to represent this reversible circuit as a dependency chain, a dependency graph. Okay, what do I mean by dependency graph? A dependency graph has a bunch of nodes. And an edge represents some information. Well, that information is collision, but there's not enough time to explain collision. But there's a way to transform this graph to this graph, where each node is a gate, and a dependency is collision between gates. Okay. Now, if you're familiar with normal compiler engineering, you understand what a dependency chain is. Like a package depends on another package, and another package. That's what it is. A gate depends on other gate. Depends on another gate, another gate. That's how we create this dependency graph. Okay, cool. So this dependency graph could be really big, right? By introducing redundancy, we have made hotspots in this graph, right? Because we have taken subsections of them out. Let's just say we take this out, and we replace this particular subgraph with a bigger graph, right? That's how we introduce redundancy. After introducing redundancy, what I'm going to do is I'm going to make it harder for you to find any redundant path. For example, if I just give you this particular circuit, after introducing redundancy, for you to be easy to find a local subsection that is a hotspot where redundancy exists and reverse it. What I'm going to do is that I'm going to try my best, like literally what they do, try my best to spread the redundancy over the other parts of the graph. I try to diffuse it out to other parts of the graph so that with polynomial number of resources, you cannot find a hotspot. And the way I'm going to do that is I'm going to randomly pick a subsection of, let's say, 5 gates. I'm going to replace it with 5 gates now. Instead of introducing redundancy, I'm just going to diffuse it over larger and larger parts of circuit. And the intuition behind this is that since I'm selecting random subgraphs and I'm replacing them with functionally equivalent with same number of gates, other circuits, it somehow diffuses other parts. It somehow diffuses the redundancy to other parts of the circuit. Okay, and that's what they do. There are 2 stages: inflation, redundancy, and then taking away the redundancy while needing. Okay. Now, and that's it. You do this many, many times, the claim is that this is secure. You will not be able to reverse it. And if you're able to reverse this, it's really nice because now you have the bounty. Okay. That's it. I think that's it.
Can I learn more about the bounty?
Go to Obfuscation.io. It has all the information where you can learn more about this bounty. And if you do you know what is Obfustopia? Just to really check, we are living in Obfustopia, by the way. Anyways, everything is possible. Yeah.
Okay, thank you, Jay, Ard, and me.
Great. Hi, I'm Tian Yao from Oblivious Labs. Next, I'm going to introduce to you something much more efficient than I/O, called Oblivious RAM, or ORAM for short. So first, let's take a look at an example in Web 2. So usually, when you register a Messenger app, the app would require you to upload your contacts so that it can match you with your friends. But as a user who cares about privacy, this immediately raises a red flag. So Signal, a messenger app that advertised privacy in their value proposition, said, no worry, we will keep your contacts private in our TE. So basically, we will have this secure processor, if you trust Intel, that will process your contacts and match it with our users' data in our encrypted database. Okay, so everything's encrypted. What can go wrong? The main issue here is that encryption doesn't hide your access pattern. So an attacker, say a malicious operating system, can guess who is in your contact list by just looking at which disk pages in this encrypted database is accessed. Even if you put the entire DB into the memory, it's still vulnerable to many side channel attacks. So a naive solution would be to scan the entire database for every batch of queries. And this is apparently not scalable. By the estimation of Signal, this will require them 500 servers to support the business. Luckily, we have ORAM to the rescue. So first proposed in 1987, ORAM can be viewed as a compiler that obfuscates the access pattern of the program. Unlike I/O, maybe I can explain it a bit more. So basically, the attacker learns nothing except like how many access you make from your access pattern. Okay, so unlike I/O, in which we are satisfied with polynomial overhead, for ORAM we can achieve polylogarithmic overhead, and it is also practically efficient. So for Signal, it reduced their operational cost from 500 servers to just 6 servers. And unlike many people think, ORAM itself does not involve any cryptography. So it is so simple that we can try to build an ORAM together in the next few minutes. Okay, let's build an ORAM. So recall that our goal is to obfuscate the access pattern. So a first attempt might be to just put these entries at random locations in the database. So this would work if you just access each entry once, but once you access the same thing twice, the attacker would know it because you also access the same physical location. So a slightly smarter approach would be to move the entry to a random new location after access it. But it still doesn't work because the attacker can trace where you move the entry to, right? But we are getting close to a working solution. So the high-level idea is instead of moving the entry directly from here to there, like taking a taxi, we let these entries take buses. So the nice thing about bus is that it always has a fixed route and schedule, no matter where you want to go. So to make yourself untraceable, you only need to hide whether you take this bus or not. And this can be guaranteed by, say, the semantic security of the underlying encryption scheme. So to make this idea work, we change the structure of the database from a vector into a tree. So each entry is assigned a random leaf node in this tree, but it is allowed to stay anywhere on the path between the leaf and the root node. So after we access an entry, we move it to a random new location. But instead of directly moving there, we first put it to the root node. So this is like a central bus station. This way, the attacker does not know where we want to go to next, right? And afterward, we perform this maintenance operation called eviction. So this eviction is this operation will allow it is performed on the entire tree. So its goal is to move the entries closer to their assigned leaves. And this eviction process can have fully deterministic access pattern. So the attacker has no idea about what their locations are. And with a carefully designed eviction algorithm, we can prove that our data structure will not overflow, except with negligible probability. So here's the animation for the eviction. So the last problem we need to solve is how do we know where the entry is in this tree? This is actually very simple. We just use another ORAM to store all the locations. And because this ORAM is smaller in size than the previous ORAM, we can keep doing it recursively until the ORAM size is small enough for just doing naive linear scan. So there are many works all based on this paradigm. So most of the work focuses on how to make this eviction more efficient. Notably, circuit ORAM is the first work that achieved O log square n overhead. And it remains an open question whether we can have a one log n statistically secure ORAM, which is the best lower bound we can prove. So for Ethereum, ORAM could have many potential applications. Generally speaking, you should consider using an ORAM whenever you need to privately access a large set of data. So a specific use case could be this private block builder to protect against MEV attacks. So the goal is to keep the transactions private before they actually got included in the block. So Flashbots, their solution is just to put the builders in TEs, but they actually also have the same issue as Signal, because the block builder needs to access the state of the chain to check the validity of these transactions. I apologize that I have been always talking about TEs for those who don't like it. So the reason why we need a TE here is that the ORAM is designed for to let a single trusted client to outsource the storage to an untrusted server. So TE here acts as this trusted single client, and it proxies all other users' requests. But if you think about it, you can achieve the same with MPC. In fact, because our ORAM does not involve running any cryptographic functions, it can be easily integrated into existing frameworks, like MP speeds. But an issue with these existing frameworks is that they're interactive. Basically, to make each RAM access, you need to have many rounds of communication between the parties, which is not scalable. So there is this more recent line of work called Gobble RAM, which directly plugs this ORAM data structure into a large Gobble circuit. So this will allow us to get constant round 2PC or MPC with slightly larger communication cost. So I think this is a potential solution for the fraud game. If you have check it out. If the private state they need is not just like 500 bits, but 500 million bits. Okay. Finally, let me give you some concrete numbers about our current implementation of ORAM. So first, for the TE scenario, to access a 100 gigabyte key-value database, the latency is about 50 microseconds. And for the Gobble RAM scenario I just mentioned, for semi-honest 2PC, it takes about 15 megabytes to access 128-bit word in a memory space of 2 to the 20. In comparison, if you do linear scan, this will cost about 8 gigabytes. So that's all for my talk. Thank you for your attention. This is a QR code you can check for the implementation. Oh, so by the way, thank you. Yeah. So by the way, if you want to learn more about ORAM, this 4 easy pieces. If you get one, you can check it in the last chapter. Yeah. Thank you. Okay. So any questions?
So I don't know who this question goes to, if rather to you or to the previous speaker.
Okay.
But if you obfuscate a program with I/O, is it still attackable by observing the memory access patterns?
Oh, so I/O. So basically, ORAM provides like a weaker guarantee than I/O. So if you have I/O, by the definition, it should already hide the access pattern.
Okay.
Yeah, but it is a good question. So for many schemes like FHE or like MPC, these cryptographic protocols, so they also need to have this like memory access pattern issue.
Yeah.
So in many cases, it is not considered right now because these cryptographic schemes are already so slow. So if you add an ORAM to it, it adds more overhead. But for like TE, because TE itself does not have much overhead, so the first use case of ORAM happens at TE. But yes, you're right. So like for all other cryptographic protocol, whenever you need to privately access a large state, you should consider using an ORAM. All right. Any other questions? I guess we are running out of time. Yes, please.
So a very fundamental question. So you mentioned that when you are using ORAM and you are in a tree structure, you are moving the data from the leaf node to the root node, and then you do a maintenance operation which redistributes it. So can an attacker not, and because that is deterministic, can an attacker not track like what root node had access to? Like if you in the example you had DB2 moving to the root node, so if it was monitoring that location for DB2 and it now knows that it moved to the root node and now it can deterministically know where the next location is, isn't that again a reversible path?
So are you talking about like when you access this entry, you reveal from which leaf you access it?
Yes.
Yeah, this is fine because whenever an entry is accessed, it's moved to a independently random new location. So it's fine to reveal to the attacker where you read this entry from. It's just you cannot tell the attacker where the new location is. So to do that, we first move it to the root node, which doesn't reveal anything, right? You always move to the root node, and then you do these evictions.
So like, is the moving to the root node randomized? Because
no, you don't
if
need
it's just after the access, then the attacker knows, right, that this was accessed and now it has been moved to the root node.
Well, you can reveal that this leaf node is accessed.
Okay.
It's fine. So basically, it's like a one-time pad in some sense. So you because you only access it at this location once, so it's fine. Okay, if there's no question, I think it's the end of this workshop. Thank you for attending. Yeah, it's amazing to have you here. Yeah.